Right now, while you're watching this video, there is an invisible shield between you and space. You can't see it. You can't feel it. You never think about it. But it's there, stretched thousands of miles above your head, continuously deflecting a stream of charged particles that would otherwise reach the surface of this planet. Without it, Earth's atmosphere would be slowly stripped away exactly like what happened on Mars. Without it, the radiation hitting the ground would make life as we know it impossible. That shield is cracking, not in a disaster movie. In the real data that European Space Agency satellites have been transmitting for 11 years, there is a region of roughly 15 million square miles stretching from South America to Southern Africa where Earth's magnetic field is 3 times weaker than the global average. That region has been growing for decades. And since 2020, it has started doing something nobody predicted. It is splitting in two. NASA is watching it. ESA is watching it. The engineers who operate satellites in low Earth orbit know about it because their machines glitch every single time they fly over it. What nobody has really explained is what is behind it. What is happening 1,800 miles beneath your feet? What it means that it is accelerating, and what this planet's own history tells us about what happens to a magnetic field when it starts behaving exactly like this. That is what this video is about. The facts alone are enough to change how you look at the sky tonight. The Bermuda Triangle of Space. The Hubble Space Telescope is the most expensive scientific instrument ever built. It has photographed galaxies billions of light years away. It revealed that the universe is expanding at an accelerating rate. It changed how humanity understands its place in the cosmos. And 10 times a day, it is forced to close its eyes. Not because of a malfunction, not because of a mechanical failure, because it flies over a specific region of the planet, and in that region, its most sensitive instruments would not survive if left switched on. Engineers on the ground send the command to shut down its UV detectors at every pass. Hubble loses 15% of its total observation time because of this single zone, an hour and a half every day, the most expensive space telescope ever built, blind above the same patch of sky, orbit after orbit. In certain circles of aerospace engineering, that region has a nickname, the Bermuda Triangle of Space. That is not an exaggeration. In 2007, several satellites in the Globalstar constellation were knocked out of service by radiation while passing through this zone. Their processors were hit by what engineers call single-event upsets, high-energy particles that pass through an electronic component and flip a bit in memory. A 0 becomes a 1. A correct calculation becomes a catastrophic error. On the ground, this almost never happens because the magnetic shield filters out the vast majority of these particles before they reach the surface. Over the South Atlantic, the shield is so weakened that the particles descend all the way to the altitude of satellites in low Earth orbit and pass straight through the hardware as if the shielding were not there. Globalstar lost satellites. Millions of satellite phone calls were lost. It took engineers time to fully understand what had happened, because this type of damage was difficult to anticipate from the ground. You could not see the particles, you only saw the systems going down. The IS experiences computer crashes every time it passes over this zone. So did Skylab. So did the Space Shuttle. So does SpaceX's Drag. Every vehicle in low Earth orbit accumulates anomalies that happen nowhere else along its trajectory and happen every single time, above the same region. That is why IS spacewalks are specifically scheduled to avoid coinciding with a pass over the anomaly. That is why the station has reinforced shielding directly above the sleeping quarters and the regularly occupied spaces. This is not a theoretical precaution. It is a direct response to something that happens in reality, on every orbit. Until very recently, it was manageable. Engineers knew where the zone was, roughly how big it was, and they worked around it. What changed is that the zone is no longer staying where it was. What astronauts see? Picture yourself on board the IS. It is 3 in the morning, station time. You are inside your sleeping bag attached to the wall. The lights have been off for hours. Your eyes are closed, and you see flashes. Not 1, not 2. Sharp white flashes across your field of vision, with no light source anywhere nearby. Eyes open, eyes closed, it makes no difference. The flashes are still there. This is not a dream. This is not a hallucination. Dozens of astronauts have reported it since the earliest crewed missions in orbit, and scientists know exactly what it is. High-energy particles, galactic cosmic rays, protons ripped out of the solar wind pass through the steel and aluminum walls of the IS as if they do not exist. They pass through your skull, and they strike the cells of your retina directly, triggering a visual response that your brain interprets as light. Because to your brain, there's no difference. A retinal cell activated by a photon from a lamp and a retinal cell activated by a proton from deep space send the exact same signal. It is called phosphenes. You have probably created them yourself without knowing it. It is exactly what happens when you press hard on your closed eyes and see colors and shapes. The mechanical pressure activates retinal cells, and the brain reads it as light. This is the same thing, except the pressure is a particle from space, passing through inches of metal and bone before reaching your retina, and there is absolutely nothing you can do to stop it. It happens in low Earth orbit all the time, at low levels. Above the South Atlantic anomaly, it intensifies because the particle flux is denser. The radiation dose measured inside the IS in this region can reach several hundred microgray per minute at the heart of the zone compared to roughly 280 microgray per day on average across the rest of the orbit. It is a concentrated, brief exposure that repeats at every pass. Over the course of a mission, it adds up. The astronauts sleeping above this zone sleep behind additional shielding panels, not for comfort as necessary protection against something the instruments register every single time. There is something else that astronauts do not always say publicly: the accumulation. A single exposure to elevated radiation is not necessarily catastrophic, but astronauts spending 6 months on the IS pass over the anomaly dozens of times per week. Each pass adds a dose. Over the course of a 6-month mission, the total exposure above that zone accounts for a meaningful portion of the radiation quota allowed across an entire spaceflight career. That is why space agencies have strict lifetime limits on how many missions an astronaut can fly. Not because space is generally dangerous, but because this specific region of the planet is dangerous every single time, and that danger compounds. The shield that is cracking our shield has a hole in it, and since 2014, that hole has grown by an area roughly half the size of the European continent. To understand how serious that is, you first need to understand what the shield actually does. Earth's magnetic field is not something abstract. It is a real physical structure, generated at the core of the planet, extending tens of thousands of miles into space, continuously deflecting what the sun sends our way and what deep space sends our way. The solar wind, which blows constantly outward from the sun, is made up of charged particles traveling at hundreds of miles per second. Without the magnetic field, they would strike the atmosphere directly. Look at Mars to understand what that looks like over the long run. Mars lost its significant magnetic field roughly 4 billion years ago. Its core cooled, the dynamo stopped, and without a shield, the solar wind did its work. It stripped the Martian atmosphere away, molecule by molecule, over billions of years. Mars's atmosphere today is 100 times thinner than Earth's. There is no liquid water on the surface. Ultraviolet radiation hits the ground directly. And there is almost certainly no life, at least on the surface. That is what it looks like when the shield disappears not over years, but on geological timescales. Our shield has a hole. There is no question of immediate disappearance, but the hole is real, measurable, and it is growing. The South Atlantic anomaly covers a region where Earth's magnetic field is roughly 3 times weaker than the global average. Particles that should be deflected toward the poles instead penetrate far deeper into the atmosphere here down to the altitude of satellites in low Earth orbit, at 250 to 300 miles up, where radiation of this intensity should not exist. The data from ESA swarm satellites is unambiguous. Between 2014 and 2055, the zone grew by an area equivalent to half the European continent. That is not a rough estimate. It is the result of 11 years of continuous magnetic field measurements by 3 specialized satellites doing nothing else since their launch. And since 2020, something new has happened. Instead of simply expanding, the zone has started splitting. Where there was once a single center of maximum weakness, there are now 2. The first is still centered above South America, as before. The second is developing further east, off the southern African coast, and the data shows it continuing to individualize. 2 holes in the shield, not 1. And models built from the swarm data suggest this split is not going to reverse anytime soon. There is one more detail that most articles do not mention. The zone is also moving. It drifts westward at roughly 12 miles per year slowly, but in a direction that is not changing. If that drift continues at the same pace, within a few centuries the main zone will have shifted thousands of miles from where it sits today. The geography of orbital risk will be different. Trajectories that are safe now will not be. And the trajectories that will be safe are difficult to calculate as long as nobody fully understands what is driving this drift from the core. For the engineers managing satellite constellations in low Earth orbit, that means recalculating 2 high-risk zones instead of 1, with uncertainty about how both lobes will continue to evolve and drift. For space agencies, it means planning missions around a radiation environment that is shifting shape and position beneath their feet. And to understand why any of this is happening, you have to go down. What is happening 800 miles beneath your feet, roughly 1 mile 800 miles beneath Africa? There is something as wide as an entire continent that nobody has ever seen directly that has been there since before the dinosaurs. That structure is disrupting Earth's core. And it is what is ultimately causing the satellites to crash. Earth's magnetic field is not generated at the surface. It is generated in the core, specifically in the outer core, a layer of molten iron and nickel at roughly 9,000 degrees Fahrenheit, slowly turning around the solid inner core driven by the planet's internal heat and rotation. That movement of liquid metal creates an electric current, and that current generates the magnetic field. This is called the dynamo effect, the same basic physical principle as an electrical generator, but operating at a planetary scale. The process is not static. The liquid iron in the outer core moves in complex currents that shift slowly over decades and centuries. And at the boundary between the core and the rocky mantle above it, roughly 1,800 miles down, far deeper than anything humans have ever drilled, something is disturbing those currents. Beneath Africa, at that depth, there is an unusually dense mass of rock. Geophysicists detect it through seismic waves. When an earthquake occurs anywhere on the planet, the waves passing through this region slow down in an unusual way, as if the rock has a different composition from the surrounding mantle. The structure has a technical name, the African Large Low Shear Velocity Province, and its scale is extraordinary. A mass the size of an entire continent, buried at a depth that nothing humans have ever built could come close to reaching. Some researchers believe it is a remnant of ancient ocean floor that sank into the mantle hundreds of millions of years ago during tectonic subduction and has been accumulating at the core mantle boundary ever since. If that is the case, this structure has been there longer than the dinosaurs. It almost certainly predates the first vertebrates on Earth. What this mass does to the magnetic field is that it disrupts the movement of liquid iron directly below it. It creates a region in the core where magnetic field lines exit in the wrong direction inward instead of outward. That produces a zone of weakness that propagates upward through 1,800 miles of rock, crosses the crust, rises into the atmosphere, and shows up at satellite altitude as a region where radiation pours through. Archaeomagnetic studies measurements of the magnetic field preserved in volcanic rocks and ancient fired ceramics over the centuries show that this underlying anomaly is recurring. It has appeared at least 3 times in the past 2,000 years, between 400 and 450 AD, between 700 and 750 AD, and between 155 and 5050 AD. Each time, it comes from the same place. The structure beneath Africa has not changed. What changes is the intensity with which it expresses itself. Satellite measurements have confirmed an acceleration in the phenomenon since 2020. Why now, at this intensity, at this pace? Nobody has a satisfying answer yet. The global field is losing strength. The South Atlantic anomaly is not a local accident. It is the most visible sign of something broader. Since 1840, the first systematic scientific observations of Earth's magnetic field, conducted in part by Carl Friedrich Gauss and his global network of measurement stations, the field has lost roughly 9 to 10% of its total strength. That is not a minor fluctuation. It is nearly a tenth of the shield's full power in less than 2 centuries. For a long time, scientists projected that weakening at roughly 5 per century, slow, steady, manageable. Models predicted that even at that pace, the field would remain functional for millennia. Then, the swarm satellite data arrived, with a precision that ground-based measurements had never been able to reach. And what it shows in the most affected zones is different. In some regions, the rate of weakening is closer to 5% per decade, 10 times faster than what was calculated from the ground. At the same time, the field is not weakening uniformly everywhere. Above Siberia, it is strengthening. Above Canada, it is retreating. This is not a uniform decline, it is a redistribution. The field is changing shape. It is slowly reorganizing from the inside. And geologists have seen this type of reorganization in the planet's magnetic record before. They know what it tends to precede. What has already happened 540 times Earth's magnetic field has not always pointed in the same direction. It has flipped many times. The magnetic North Pole became the magnetic South Pole. Compasses, if they had existed, would have pointed the other way. And this has happened roughly 520 times over the past 170 million years, not as an anomaly, but as a regular feature of the dynamics of Earth's core. Geologists read it in volcanic rock. When lava cools and solidifies, the magnetic minerals it contains align themselves with the direction of the magnetic field at that time and stay locked in place for millions of years, like a photograph. By studying rock strata of different ages, scientists can reconstruct the history of Earth's magnetic field across hundreds of millions of years. The record is precise, measurable, and unambiguous. The last complete reversal happened roughly 780,000 years ago. It is called the Motoyama-Brunhes reversal. And what researchers discovered when they studied it closely is not simple. It was not a clean flip. It took approximately 22,000 years, and during that time, the field did not simply invert in one smooth motion. It first collapsed, then partially recovered in an intermediate direction, then collapsed again. Dozens of temporary magnetic poles existed simultaneously over decades. The shield was in a chaotic, fragmented state, many times weaker than it is today. Particles that normally arrive at the poles descended to far lower latitudes. The northern lights, confined today to the Arctic, would have been visible from temperate regions of the northern hemisphere. Life survived. All 540 previous reversals were crossed by entire ecosystems, entire species, entire forms of life. A weakened magnetic field lasting 22,000 years is not an extinction, but it is 22,000 years of more intense cosmic radiation hitting the surface. It is 22,000 years of impact on the ozone layer. It is 22,000 years of impossible navigation for species that use the magnetic field to orient themselves: migratory birds, sea turtles, certain fish. For us today, the question is not biological survival. It is technological. GPS works because we can precisely predict the magnetic environment that satellites move through. Modern power grids are vulnerable to geomagnetic storms. We saw that in 1989, when a solar eruption caused a 9-hour blackout across Quebec by overloading transformers. A shield 10 times weaker for millennia would be a world where those events are no longer rare exceptions. It would be a world our engineers have no procedures for, because no technological civilization has ever lived through one. The question that has been building since the swarm data started accumulating: are we seeing the early signals of something comparable to what preceded the Matuyama-Brunhes reversal? Researchers who study Earth's core are careful. Most say a reversal does not appear imminent, that similar periods of field weakness have occurred in the past without triggering a full reversal, and that the field has stabilizing mechanisms. They are right to be careful. Honest science does not dramatize uncertainty. But they also add, with the same honesty, that the average interval between reversals is roughly 300,000 years, and that the last one was 780,000 years ago. We are overdue by the average. That is not proof that one is coming soon. It is simply a fact the data does not allow us to dismiss. What continues, in the meantime, is the measurement. The swarm satellites keep orbiting. The data keeps accumulating. The hull keeps growing. And since 2020, it has been splitting in two, a signal that something is evolving in the dynamics of the core, 1,800 miles beneath your feet, in a way nobody had precisely predicted. The shield is still there, still doing its job, but it is no longer exactly what it was. And for the first time, we have the instruments to watch it change in real time. What we do with that information is a different question. What we can say for certain is that for the first time in human history, we have the tools to watch Earth's magnetic field change as it happens. Not by reconstructing the past through rock, in real time, through satellites measuring the exact state of the shield every day, every hour. And what those instruments have been showing us since 2014 is that the shield is changing. Not catastrophically, not in a way that makes life impossible tomorrow, but measurably, continuously, and in a direction that has no visible endpoint yet. The swarm satellites have a limited operational life. When they eventually stop, their successors will need to replace them to keep the monitoring going. Because this zone over the South Atlantic is exactly that, the first place where we can watch, from space, something happening inside the Earth. A signal from the core, 1,800 miles down, that travels through the entire planet and shows up at 300 miles of altitude by crashing the computers of satellites passing overhead. This is not an unsolvable mystery. It is a measurable phenomenon studied by hundreds of researchers worldwide, with data that improves every year. But the answer to the central question, is this the beginning of something larger, or just another recurring fluctuation like the ones in the magnetic record? That answer is not here yet. And that may be the most honest thing to say. We are watching something happen beneath our feet from unreachable depths, with tools we did not have 20 years ago, and we are only beginning to understand what we are looking at.